In this lecture, we are going to give the enemy the ability to check if it hits a step in the front. This is going to be a slightly more complicated lecture, but no worries, as long as you follow the steps, you're going to have no problem to do it. First, let me show you the plan. You can see there is a step in front of my enemy. By the way, if you don't have a close step in front of the enemy, you might want to add it to the tile map now. Back to the plan. I want to cast a line to trace if there is anything in front of the enemy, and the start point should be the bottom right corner of the capsule shape. Then the line goes to the forward direction of the enemy. Alright, let's go to the enemy BP. First, we need a way to get the start point. Let's drag in the capsule component. Then we can call the getComponentBounce function. The function is under the collision section. This is going to give us the bounce of the capsule in the shape of a box in a 3D world. I realize this doesn't sound very intuitive, so I want to help you understand how the bounce works by visualizing it. Let me use a function called drawDeboxBox. This function can draw a box in a 3D world to help us debug. Connect the addMovementInput function to it. So this is going to happen every frame in the game. Then we connect the origin to the center and the box extent to the extent input. We can also change the color. So let's change it to red. This is going to make it easier for us to see the box. I'm also going to increase the thickness of the box to 2. And it's okay for the duration to be 0, because this is happening every frame, since we are doing this in the event tick. Let's compile first. I also want to see the capsule component in the game, so we can compare it with the bounce. Select the capsule component and search for hidden. We can disable the hidden in-game option. Now the capsule should be visible in the game. Alright, let's go back to the level. Let's run the game to test. But this time, I'm going to do something different. I'm not going to hit the play button. Instead, I'm going to click on this simulate button. So this is a different way to run the game. The difference between playing a game and simulating a game is that when we simulate, the player controller is not involved, so there is not going to be a player in the game. But everything else are still going to work, and the physics is also going to work. So we usually simulate the game when we want to test something that does not involve the player, or maybe some physical behaviors. Another benefit is that when we simulate the game is still running in the editor, so we still have the freedom to interact with everything in the world. Alright, let me show you how this works. Alright, we can see the enemy starts walking forward, and we can see the red box, which is the bounce of the collision capsule, and we can still move in the 3D world while the game is running. Let's take a closer look at the bottom part of the box. So the starting point of the trace line should be around here. Of course, we are going to ignore the y-axis. Alright, let's stop the simulation and go back to the enemy blueprint. Let's remove the drawDebugBox node. Next, we are going to cast a line to detect if there's a step in front of the enemy. We are going to use a function called lineTrace for objects. Make sure you select this function from the list. For more information on the function, you can hover your cursor on the function. Alright, let's select the lineTrace for objects function. Let's connect the addMovementInput function to it. First, I just want to cast a line from the center of the enemy to show you how this function works. Afterwards, we're going to start working on the start point. I'm just going to connect the origin, which is the center point, to the start input. Then let's drag out from the origin again and connect it to an add node. Set x to 20. This is going to give us a new point that's to the right of the origin point. Then connect it to the end input. The next input is very important. It's called object types. This is to define what kind of objects we want to detect, and this input expects an array of channels, since you can detect objects from multiple channels if you want. Let's drag out from object types to make an array. We need to drag out from the input. This is for the engine to know what kind of array we are trying to make. You can see now we have an array with the right type. For now, it just has one channel in it, which is world static. You can hit add pane to add more channels if you want. But here we just need one channel, so I'm going to right click and remove this extra pane. Also, the world static channel is indeed what we are trying to detect because the channel of the tile map is world static. Next, we have the tree's complex input, and we don't need to worry about it. Then the next one is actors to ignore. This is the objects we do not want to detect. We can skip this input here. The next one is draw debug type. We want to set it to for one frame. And this is going to help us visualize the tracing line. And for one frame, it's good enough since we are doing this every frame. The next one here is also very important. It's called ignore self, and it's enabled by default. This is what we want because we don't want the line to detect the enemy itself. Alright, for testing purpose, let's print out some message. Drag out from the return value, connect it to a branch node. When the branch is true, we know we have hit something. All of the information about the object we are detecting is in this lHit output. So let's drag it out and break hit result. So now we can see all of the data it contains. You can see it contains quite a lot of things. For now, we just need the hit actor, which should be the tile map. Let's drag out from the true condition of the branch node. Let's call the print string node. Connect the hit actor to the input. Alright, that's pretty much it. Let me rearrange the nodes and go through this again. We cast a line from the center point of the capsule shape. Then we print out the name of the object that we are hitting from the true condition. Alright, we are done here. Let's compile and go back to the level because we need to update the tile map. Now we are shooting out a line from the center point of the enemy. Later on, I'm going to show you how to shoot a line from the bottom right corner. But for now, I just want to keep it simple and demonstrate how to use the line trace feature. But this also means we need to create a wall in front of the enemy. Otherwise, we're not going to detect anything. So I'm just going to add some blocks to the tile map. Alright, let's save the tile map and go to the level to test the game. By the way, you only want to simulate the game, because when I play the game, for some reason, the debug line is not in the correct position, but the line position is completely correct when we simulate the game. Now you can see a red line coming out from the center of the enemy. Then it hits the wall, and the part that intersects with the wall is highlighted in green. We also get the messages every frame. So it seems like the line tracing function is working perfectly. There are two other things I want to mention. First, the close background is too close to the tile map. This doesn't affect the game, but I still think we should move it away from the platform. The other thing is that you can see the collision shape of the tile map in my viewport. You might not see it on your side, but if you want to see the collision shape of the tile map, you can press Ctrl plus the C key to toggle it. Alright, let's remove the nodes for the print string function. You can also remove the branch node at the end here, because later on I found that we don't need this node, so I will delete it later on. So the next thing to do is find out the correct start and end position for the line trace node. So we're going to come back here to rework this part. Before that, I want to remove the tiles I just added to the tile map. Alright, let's save the tile map and close the tabs that we don't need. Jump back to the enemy blueprint. Let's clean up these nodes. I'm going to remove the add node and disconnect the connection from the origin to the start. Alright, let's make more space, since we're going to add some nodes here. Before we get started, I also want to quickly update the close background. So let's open the BP background. Go to the viewport. Select the close BG. I'm going to decrease the Y location from 150 to 130. Let's go back to the level and simulate the game. Alright, now it's not too close to the platform. Let's stop the simulation. Close the background blueprint. Go back to the enemy blueprint and save everything. Alright, now let's get started. Alright, let's start working on the start and end point. For the start point, We do not want it to be the center point of the capsule. We want it to be at the bottom line where the enemy touches the ground. And we also need to be in front of the enemy. So it's basically the bottom right corner when the enemy faces to the right. But the origin point is still a great place to start. So let's drag out from the origin. And we use the add function. For the b input of the add function, let's drag out from it. And we make a vector here. Alright, now let's think about this new vector. For the x value, we want it to shift toward the direction that the enemy is currently facing. So here, we can use a function called getActorForward vector. This is going to give us the forward direction of the enemy. But this is only a direction. We still need to figure out the distance we want to shift. So we want to shift half of the width of the enemy. And to get the width of the enemy, we can use the box extent output. Let's break it into 3 values. The x value of the box extent is exactly half of the width of the capsule component. Before using it, let's also break the forward vector into 3 values, because we also only need the x value. And this value should be either 1 or -1, since the forward vector is an unit vector. Sometimes we also call it a normalized vector. It's still just a regular vector, but the length of the vector is 1, since we only need the unit vector to present a direction. Alright, let's multiply the x value of the box extent by the x value of the forward vector. This is going to make sure we always get the correct shift along the direction that the enemy is facing. Then we can connect the result to the x input of the make vector node. So now we have the final x value of the start point. We don't care about the y point because we are just doing this in 2D. So next, let's figure out the z value, which is the vertical position of the start point. This time, we can make use of the z value of the box extent because it's half of the height of the capsule component. We just multiply it by -1. This way, we are going to shift downward, and we are going to get the vertical position of the bottom of the capsule component. Connect the result to the z value of the make vector node. Now we have the start point for the tracing line, and we can plug the final result from the end node to the start input. Next, we need to find out the endpoint. And this shouldn't be too hard for us, because we just need to shift the start point along the forward direction of the enemy. So let's start with the origin point again. Drag out from the origin point. Also use an end node to add a shift to it. Drag out from the other input of the end node. We can also make a vector here. Let's connect the final z value for the shift vector to the z input, because the vertical position should never change. So we just connect this one to the z input here. Next, we're going to figure out the x value. Let's drag out from the x value of the forward actor. Then multiply it by 1.5. Then we add another pin to the multiply node. Then we multiply by half of the width of the capsule component. So the number 1.5 is going to make this value shift forward a little bit more. Now we can connect the result to the x input. Alright, now we have the endpoint. Let's connect the result of this add node to the end input. We're all done here. Let's go back to the level and simulate the game to test. Alright, the tracing line is in the correct position. We can see the line is coming out from the bottom right corner of the enemy, and now it completely goes into the step. So the line is all green, and the red dot here is the contact point. Let's stop the simulation. I want to test the other direction. Let's select the enemy and go to the details panel. Let's set the Z rotation to 180 degrees. Now this enemy is facing left. Let me simulate the game. We can see the red line is indeed in the right place. For now, the enemy just falls down, no problem. Let's go back to the enemy blueprint. Let's clean up these nodes. Let's select all of the nodes regarding the start and end points. Right-click, select Collapse to Function. Now these nodes are packed inside a function. let's rename the function first. I'm going to call it getLineTracePoints. The function has two outputs. Let's also rename them. The first one is the start point. I'm going to call it forward_start point, because later on we are going to have points that go downward to detect if the enemy is at the edge of the platform. That's why I put the forward prefix here. This is to differentiate these 2 points from the downward points we are going to create later. I'm going to call the second one forward_endpoint, because now this is a function. We need to connect it to the control flow. Otherwise, nothing is going to happen. We can also go into the function by double-clicking on it. You can see these are the nodes from before. We don't need to change anything here. The point is, whenever you have too many nodes, you can pack the nodes for the same purpose into a function. This is going to keep the graph as clear as possible. We also want this function to output another 2 points for the edge detection. Let's select the return node of the function, add 2 more outputs. I'm going to call the first one downward_start_point, and the type should be vector. For the second one, let's call it downward_endpoint. Also, don't forget to change the type to vector. We are going to cast a line downward from the same point as the forward line, and this second line is going to detect if there is a ground tile that's in front of the enemy, so the enemy can walk onto it. For the downward start point, it's exactly the same as the forward start point. So let's just connect the same vector to it. I just realized there is a typo in the downward endpoint. Let me fix it. Alright, next, let's think about the downward endpoint. This one is also very easy. We just need to shift the start point downward. So let's drag out from the start point again. Then use the add node. Then we change the z value of the second input to -30. This is going to shift this vector downward. Then we just connect this one to the downward endpoint. Alright, now we have the 2 new points. Let's compile and go back to the event graph. We need another line trace for objects node. So let's just copy and paste the existing node. I'm going to delete this branch node at the end, since we don't need it for now. Then connect the first line trace node to the second one. Also, don't forget to connect the object types. Then we can connect the downward start point and the downward endpoint. We are finished here. Let's compile and go back to the level. Let me turn the enemy back to the right. Otherwise, it'll just keep walking, and that is going to make it hard for us to check out the lines. Alright, now let's simulate the game. Great, we get a downward tracing line. For now, it's too long, and this is unnecessary. So let's make it shorter. Let's go to the function and change this value from -30 to -10. Let's test again. Great, the 2 lines are exactly what we need. One last thing, if you get closer, you're gonna see there is a space between the capsule of the enemy and the ground. We do not need to worry about this gap. I think it's created by the character class to avoid some imperfections and jitterings in the movement. Alright, let's go back to the enemy blueprint to recap. We have this function that generates 4 points for the trace line nodes. Then we use 2 line trace nodes in the event graph to cast a tracing line forward and another one downward. Alright, this lecture is already getting too long. Let's rotate the enemy in the next lecture.